Discuss the continuity of the following function. If there is a removable discontinuity, describe how this can be removed. So the function is defined in a piecewise manner. F of x equals sine x over x when x doesn't equal 0, so everywhere but 0, but f of x equals 0 when x does equal 0. So that's quite a tricky sounding function. Calculator paper, so I would go straight to the calculator. Make sure you're in radian mode whenever you're dealing with sine, because at this level this is a radian thing. You need to make sure you're in radian mode, so I will do that first. And I am in degree mode, so I need to make sure I'm in radian mode. Go out, and I need to draw sine x over x. And I'm not going to bother with the piecewise bit. I think I can plot y equals 0. So I'm just going to write sine x over x. Okay, so that's an interesting looking function. I think that'll be okay. So we're really interested in this bit here. It looks like it's going to be fine everywhere else. You just think of sine of x is defined everywhere anyway. Sine of x itself is a perfectly continuous function. The problem with this is when x is 0, you'd have to divide by 0, so that would be an issue there. So if we just have a look on here, and if we just trace and put in x equals 0, you can see y is an error. So for this sine x over x, when x equals 0, it would be undefined. So that's presumably why there is this piecewise definition. So it's been given a value when x is 0, but it doesn't look like it's the same value, which is where we're going to have an issue. So if we draw a little picture of it, it looks like we kind of peak here. It looks like it goes up to somewhere around 1. Here, and it's, remember, at 1, and we can use the trace function, and just you can see it's very close to 1 that side, and it's very close to 1 that side. We'll talk about the actual limit in a minute, but it's definitely not defined there, but I'm going to say that's 1, and then it looks like it sort of goes, we'll just draw the bit we want up to here, something like that. Down again, and then it's just going to keep being continuous for the rest of it. We're really interested in this bit here. So that's the function. So what f of x? Nearly, but then we need to include this other bit. It says f of x equals 0 when x equals 0. So it's undefined here, but the actual f of x itself is defined because of this piecewise bit. So already you can see this is definitely a discontinuity, but we need to think about this limit. So the limit as x approaches 0 of f of x. Now hopefully you recognize that this is the limit as x approaches 0 of sine x over x, which we should recognize is the fundamental trigonometric limit. So that equals 0 equals 1, and that is because of the fundamental trigonometric limit. Trigonometric limit. So, to be continuous at a point x equals a, firstly the function needs to be defined at x equals a. Secondly, the limit as x approaches a of f of x needs to exist, and it needs to be equal to the value of f of x at that point. So we've only got one issue here, is the fact that f of 0 does not equal the limit as x approaches 0 of f of x. So this is it's a discontinuity, but it is a removable discontinuity. Everywhere else in this function it's defined. So f of x is continuous for all real x apart from x equals 0, and we have a removable discontinuity. Removable discontinuity at x equals 0. Remember, we know it's removable because the limit of f of x as x approaches 0 does exist. If it didn't exist, this would be an essential discontinuity. So we have been asked, if there is a removable discontinuity, which there is, describe how this can be removed. So we're going to define a new function, the discontinuity. Can be removed by defining a new function g of x g of x. Right, where g of x equals, so we're still going to use the piecewise things. Basically, we need to make sure that the value of g of x equals 1 when x equals 0. Everything else stays exactly the same. So g of x equals, so get your curly brackets, sine x over x, and that is for x doesn't equal 0, so everywhere else. But when x does equal 0, well, it needs to equal 1 when x does equal 0. And this actually is not the same as just calling it sine x over x, because that would still have a discontinuity when x equals 0. So this function is actually now continuous across its whole domain for all real x.